Okay, hello everyone, and welcome to our second climate snack. My name is Cesar Terrer. I'm an assistant professor in the Department of Civil and Environmental Engineering at MIT. The seminar series are meant to be dynamic, like interview-like discussions on climate change topics, hopefully accessible to non-academics, academics from all disciplines, and pretty much everyone. This webinar will be recorded, and thank you to Ana do Campo for running everything behind the scenes. If you have questions for the speaker, please use the chat box, and we will formulate some of these questions in the Q&A section and at the end. After having had Josh Fisher here a month ago now, today I'm very excited to present Asmeret Asefaw Berhe, talking about soils and climate change. Asmeret was born and did her undergrad in Eritrea. And after that, she came to the US and graduated from UC Berkeley. Currently, she's a professor at UC Merced and nominee to serve as the director of the Office of Science at the US Department of Energy, DOE. Now, Asmeret, going to your topic today, I really like the title, What's Soil Got to Do with Climate Change? I think it's provocative. As you know, for many people, soils are just this, almost lifeless system where nothing really happens, just dirt. Even to some scientists, soils are just treated as a black box where plant inputs end up. And people assume that soil processes are just so slow that their influence in the climate system in the short term, at least, is negligible. So please, Asmeret, if you could talk a little bit about the role of soils in regulating the climate.
Yeah, thank you, Cesar, and everyone for the invitation to join you all today. I'll start by sharing my screen, which I think might be a little helpful to use a few graphics to explain the conversation, that some of the things I'm talking about. So as Cesar indicated, a lot of times in the climate discussion, there's this tendency to boil down the issues to just the amount of greenhouse gases that are being released by fossil fuel burning in the atmosphere, and the fact that they're increasing the atmospheric concentration of CO2 and other greenhouse gases. I think it's very important to think about the fact that, first of all, that CO2 that's being released into the atmosphere and other greenhouse gases doesn't just come from fossil fuel burning. There is also some release of greenhouse gases from land use and land cover change that occurs, in particular things like deforestation that have had important implication on the amount of greenhouse gases we keep releasing in the atmosphere. And secondly, I think it's also really important to think about the fact that the rate at which the atmospheric concentration of CO2 has been increasing is actually half of the amount that of the amount of CO2, for example, that we've been releasing to the atmosphere. Which basically means that we're getting about 50% discount on our actions, right? And that 50% discount or so that we're getting is thanks to the natural ecosystems, the land ecosystem that is sequestering about a quarter of the CO2 that we keep releasing into the atmosphere every year, and the oceans that do roughly about similar amount of sequestration too. So if it wasn't for these natural ecosystems that are able to take out atmospheric CO2 and store it in pools that cycle at slower rates in either the land or the ocean ecosystems, you can imagine then that the concentration of CO2 in our atmosphere could have been growing even faster. And so the natural ecosystems, and especially on the land, what soil supports, have major roles to play here, both on the amount of CO2 that keeps getting released to the atmosphere, as well as how much is taken up out of the atmosphere. And as I say that, I want to take us back to just the simple basics here, right? Is that on any given time scale, plants are taking out CO2 from the atmosphere during the process of photosynthesis and using that CO2 to build their biomass. And once these plants build their biomass using the CO2 that they took out during photosynthesis, then the plants live and die, or the other organisms that fed on the plants also live and die, and their residue enters the soil, and that's kind of the main mechanism by which carbon makes its way into soil. And I want to make sure that we're clear about the fact that all of that carbon doesn't just sit in soil. Most of that carbon actually decomposes by the activity of microorganisms in soil and is released back into the atmosphere through the process of decomposition, which release CO2 and other greenhouse gases. But some of that carbon, represented by this arrow that I think you can see on my screen at the bottom, right? Some of that carbon, though, is routed into even slower cycling pools of carbon in soil, which basically means that a small amount of carbon, even relatively speaking, that doesn't get decomposed because it finds itself in association with the soil, and soil minerals help build the soil carbon bank. What I'm trying to say here is basically that this analogy of a bank is a really important way for us to think about how the soil carbon pool operates, right? Because it's like it's like our bank account, right? In the beginning of the year, we have, or in the beginning of the month, I should say, for those of us who get a monthly paycheck, right? We have a lot of carbon, and that's what would happen when there is a lot of dead residue that enters the soil. But there is a maintenance of our life processes that need to happen, which is modulated basically in this case, represented by decomposition, and we pay our bills, and some of that some of that amount that we've had on the bank is no longer there. And so what ultimately matters for the size of our bank account, though, like the amount of carbon stored in soil, is this balance between how much is coming in and how much is coming out. And that is, if there is more coming in than coming out in this carbon balance, then we have a balance that's growing in soil. And you could take this one step further and think also about the fact that not all carbon is stored the same way in soil, right? Some carbon, as we've already talked about, rather decomposes fast. And that's the carbon that is not associated with minerals in soil. But the carbon that actually finds itself as in these organo-mineral associations, represented in this kind of blown up kind of image of either inside these aggregates of mineral particles or chemically bound to the surfaces of minerals, though, that carbon persists in soil for hundreds of years and sometimes even millennia, because it is incredibly hard for microbes to actually break the aggregates or release the carbon from these kinds of chemical associations. And so because of that, the soil system is able to store a lot of carbon. And in fact, we know that there's twice more carbon now stored in the atmosphere and in the soil compared to the atmosphere and vegetation combined. And as a result, any small change in the amount of carbon stored in soil can have a really important implication for maintenance of the atmosphere.
Asmeret, so sorry to interrupt, but why not all carbon in the soil is in this mineral associated protected form? What is the main driver of this protected carbon, and why not all the carbon is equal in soils?
Yeah, so how much of that carbon can enter into these organo-mineral associations depends on, first of all, the type of soil that we have and the mineralogy of the soil. So technically speaking, you need, for example, to form aggregates in soil, you need either clay particles or polyvalent cations that could serve as binding agents. And this can include things like calcium, for example, or other polyvalent cations that are able to bind to negatively charged organic matter particles and build these aggregates together. Or you need plant roots and fungal hyphae, all that entanglement to actually support aggregate stability. And when it comes to the chemical association of organic matter with the surfaces of reactive minerals, you need reactive minerals. Now we're talking about either phyllosilicates, these highly weathered products, soil particles that are products of extreme weathering or a high extent of weathering is what we're talking about, right? Clay particles, you need those that have charged surfaces and high charge density to be able to form chemical bonds with the organic matter. And so the primary constraint on how much of the carbon can be stored in these rather long-lived pools of carbon that cycle slowly is gonna be the type of soil and the availability of the minerals. Does that make sense?
Yeah. But is there any influence if the carbon comes from wood versus fine roots or fungi?
Yeah, so this is, as you know, a pretty interesting area of study that has been growing, that's been gaining a lot of attention in the last 2 decades or so. And part of this is that, we previously assumed that, above ground, all the carbon that falls from above ground vegetation, for example, equally contributes to, say, carbon storage in soil like roots. That doesn't seem to be the case. We keep seeing evidence that, in fact, carbon derived from below ground components could potentially be more able to stay in soil in long-term cycling pools. And different organic compounds also have different composition and functional groups that are able to form chemical bonds with a variety of soil minerals. And I should also say under a variety of environmental conditions. So all of that dictates to, so the type of minerals that you have, the type of organic matter, which to some extent depends on where it's coming from and what kind of vegetation or microbial source it's coming from. And the environmental conditions, all of those interact to dictate to what extent you have carbon that is going to be existing in these protected pools in organomineral associations versus just free particulate organic matter.
Right, thank you. So using your analogy of the carbon bank, it seems that we've been withdrawing too much carbon in the last few centuries, especially with agriculture that has depleted soil carbon stocks by more than 100 petagrams of carbon. So Asmeret, could you talk a little bit about what's this equilibrium in carbon storage in soils, and what can we do to increase soil carbon stocks to mitigate the effects of climate change?
Yeah, so maybe I'll talk about what has agriculture done and kind of the way we've used land in particular first, and kind of the implication, and then jump to the what can we do at this point, right? So if you think about how we've been using soils in global agriculture, for example, our growing demand for food, feed, and fiber in the natural ecosystem, and our growing demands from soil has meant that we've been practicing highly intensive agriculture, increasingly more intensive agricultural practices that have been extractive as far as soil resources are concerned, and causing large-scale degradation of soil. That's what you see in this map, for example, is the type and severity of degradation that world soils are experiencing. And what that means is that all of these soils that have been used, overused, and abused have seen considerable change in soil carbon storage. And many of these soils, especially in agricultural systems, as you've alluded to, have lost upwards of 100 petagrams of carbon that used to be in soil that was released to the atmosphere, as we saw from Jan Sonnenmann's work and others recently. And so that's really important to think about in our efforts to think about even the soil carbon as one of the natural climate change solutions. one of the things that I like to inject in this conversation is a point of caution, right? Before we jump into thinking about how and why soils conserve and soil carbon sequestration can serve as natural climate solution, I think it's important to talk about some cautionary tales, right? And a particularly important cautionary tale exists in the soils of polar environments, circumpolar environments, in general, Arctic ecosystems, soils that bear a permafrost or permanently frozen layer underneath. The reason why these soils are important is because they store close to a third of the world's soil carbon reserves. And they're able to do so because during the rather short growing season in these ecosystems, plants are able to photosynthesize, and they're able to, then when they die, their biomass is able to return to soil. But the environment remains rather cold and dark for most of the year for the heterotrophic microbes that are effective in degrading organic matter and in carrying out the process of decomposition. So as a result, carbon had been piling up and accumulating in these ecosystems for, over geologic time periods at this point. But right now, with warming, though, when we see rather rapid thawing and draining of these permafrosts, it's kickstarting a fast rate of decomposition and a release of greenhouse gases, both methane and CO2, depending on the resultant hydrology of the landscape. And of course, that causes even further warming, which means a positive feedback loop. So the concerns, I think, with land degradation don't just end in traditional agricultural soils in just the temperates and the tropics is what I'm trying to highlight, right? But
so Asmeret, this is a very clear, a classic example of a tipping point. As you know, it's a point beyond which a rapid increase in carbon dioxide emissions, and with that, a rapid increase in temperatures can occur. So do you know what's the tipping point for thawing, and do you know if 1.5 degrees is safe?
So I think it's, as someone recently in connection to the COP26 discussion said, it's important to say that, to highlight that these 1.5 discussions, for example, don't actually capture the reality of what's happening in most parts of the world, right? We expect that some of these Arctic ecosystems, even in a world where temperatures increase by average about 1.5 degrees C, some of these ecosystems that bear permafrost, higher latitude ecosystems might see an even faster rate of temperature increase, right? 4, 5, 6, and even more degrees centigrades increase. And it's clear that, the average 1.5 is a point where we avoid a lot of the, kind of really significant tipping points for many, many ecosystems. But in some cases, many of the ecosystems have already seen something close to 1.5 and have already approached, if not, are getting ready to approach these 1.5 and other tipping points. And on Arctic ecosystems like this are one of those examples, right?
Yeah, thank you.
Yeah.
So,
Yeah, do you want us to, okay, so we could keep talking about then, how does then the soil carbon sequestration as a natural climate change solution fits in, right? So I assume you've all seen a figure that looks something like this, where the CO2 concentration in the world's atmosphere has been fluctuating, over the last 100 million years or so ago, where we have records and modeling data that we can extrapolate to. And we also have, going forward, kind of beyond the blue line, if you will, on the panel to the right, we have a path forward that depends on what we choose to do with how we choose to intervene in this issue going forward. If we would like to achieve a warming that is below 1.5 degrees C by the end of the century, I think there's a growing consensus now that it means we can't just be talking about reducing emissions of CO2 from fossil fuel burning. We also have to be talking about adoption of climate smart land management and ecosystem management practices that take out CO2 from the atmosphere and contribute for kind of increasing the health of the soil ecosystem that makes that possible, right? And so it's important then that we achieve, even if we say the business as usual scenario is hopefully something we end up actually averting, and we don't get there. But if we do, remember that the CO2 concentrations that some estimate could be a result of this business as usual scenario is something the world has never seen in the last 100 million years or so ago. But even the scenario that is more middle of the road, just reducing emissions alone, is still a scenario where the CO2 concentrations that we would have to live with by after the end of this century and the coming one is considerably higher than what the world has seen throughout most of the last 20, 30 million years ago. But we could obviously bend the curve and achieve a much more sustainable future if we were to be able to adopt these climate smart management strategies. And there's many ways to think about how do we actually achieve this climate smart management strategy. I like this kind of animated figure that the folks at the World Resource Institute put together, which is a compilation of all the different types of natural climate change management strategies that could be achieved, and how their benefits can add up basically to help us avert, to help us achieve a limit of temperature increase that doesn't go above 1.5. So what is needed to achieve the 1.5, basically speaking. And in this colored kind of figure then, a lot of the soil-related interventions are included in the green and somewhat the yellow and orange colorations. But you could also argue that the improved livestock and rice cultivation that is in the lighter red here is also very related. We could achieve a lot if we could just reduce deforestation in the first place. And then in addition to that, all of these other land management practices. And I want to be clear about the fact that not every management intervention that is climate smart has the same potential of sequestering carbon from the atmosphere, at least not at the same rate, right? It all depends on, again, the environmental conditions, the climate envelope under which these management practices have to be occurring, but also the nature of the ecosystem itself. So for example, if you see at the bottom of this figure here, restoring histosols, that's referring to restoring organic matter-rich soils that are common in wetlands, wet environments in general, coastal margins, mangroves, that they have the highest rate of greenhouse gas reduction or removal rates, as you could see here. But we also have to be practical about the fact that the climate envelope where these types of ecosystems occur is rather narrow. So the combined benefit of this really fast rate of carbon sequestration with appropriate interventions is upward limit is about the higher limit is about 1.3 petagrams of CO2 equivalent per year, which is good, right? But there's a whole lot of interventions on the other end of this figure for me, where yes, their potential for greenhouse gas reduction is not as high as that, say, for restoring histosols. But because they can be practiced over a large area, they can achieve similar overall rates of CO2 sequestration. And I kind of will stop here, but if we want, we can talk about the 4 per mil and others.
Yeah, I have one question, Asmeret. So these 3 gigatons of carbon that the 4 per mil initiative, I think we could restore in soils. So I think that they assume that we should restore every inch of soil globally by 4 per mil, right? So, but how do we increase carbon stocks in in tropical soils or in Yosemite or the Grand Canyon, in areas that are perhaps not so easy to manage as croplands?
Yeah, I think, yeah, I like to frame this conversation on the 4 per mil, which for those who might not be too familiar with that terminology, it's this effort that started in France, that's kind of spread to all over the world now, which argues that if we manage to increase the amount of carbon stored in soil by 0.4% or 4 per mil per year going forward, that could offset about a third of all the global emissions of CO2, fossil fuel derived emissions in particular of CO2. And that's an aspirational goal, which means it assumes, like Cesar said, that we're able to achieve this rate of carbon sequestration across the world, right, in all sorts of different ecosystems, and that we're deploying all of these climate smart land management options optimally wherever they're appropriate across the world, right? But there are some realistic, some economic, some natural challenges where that actually can prevent us from doing it in one place or another. And that's all true. And I don't think anybody would debate against that. But rather, what I think is important to remember is that anything above what we're doing right now, anything that moves us in the direction of restoring soils so that they start getting closer to their carbon sequestration potential, is still a positive goal and is still helpful for both increasing the carbon storage in soil for the benefit of climate change mitigation, but also restoring the health of the soil, which is really critical for food and nutritional security of the growing human population, as well as for the livelihood of pretty much every form of living matter on land, right? So I see that, I find it maybe a bit more productive to think about, we should still pursue them, even with the challenge, pursue all of these options to our best of our ability, wherever they're appropriate, obviously, because I think it's important that the benefits that we gain from that are still a win-win, even if we don't achieve the exact 4 per mil mark across broad all ecosystems that we necessarily wish or would like to, right?
Yeah, totally agree. I have one further question that is, I know it's pretty uncertain, but I'm curious about your opinion. So how much carbon can soils contain? I mean, if we manage to restore soil carbon in all degraded areas, once we do that, can we increase soil carbon beyond that? In other words, was carbon in soils before human intervention at a steady state, equilibrium, or like at a saturation point, or can soils store even more carbon?
Yeah, I agree. I'll start with the same statement that you made, that this is a quite interesting thought exercise, but it's also a bit uncertain, right? So I agree with your framing of that. So, I think we all agree that it would be really great if we could restore all of the carbon that was in soil pre-extensive human intervention. That would take us a long way. But beyond that, we do have, I think, some uncertainty about what is the saturation limit. And so where do soils reach their highest potential for carbon storage? And we know that in mineral soils, that limit tends to be at least approached, if not reached, within reasonable time scales, because we've had the long-term experiments of organic matter addition from residue or different sources over long periods of time that haven't led to additional carbon storage in soil, right? But I think it's important to qualify that with a little bit of caveat. Like, a lot of those studies that looked at to what extent carbon storage did not increase beyond a certain level, because we presume that soil has achieved saturation, didn't actually look at, for example, deep soils, soils that are typically below 30 to 50 centimeters. So we still don't actually know, if we took a whole profile accounting of soil, whether that idea of carbon saturation that we've been, people have been observing and modeling and all of these kind of things, whether that still holds. But we also know that there are certain types of ecosystems that don't seem to easily achieve steady state, partly because they are, say, at a geomorphically lower point, terrestrial depressions, hollows, floodplains, wetlands that continuously receive carbon input, right? They tend to build up their soil carbon storage considerably higher, their storage potential and their saturation limit tends to be considerably higher than, say, their related soils that are just a little bit higher elevation, that don't necessarily experience the continuous input from deposition. So in my earlier life, I used to study a lot about the role of erosion in carbon sequestration, at a catchment scale versus the global implication of this process. And it's pretty clear that there is a lot of carbon in depositional settings. And that in depositional settings, by that I mean floodplains, reservoirs, lakes, interterrestrial ecosystems, right? And those systems don't seem to obey this idea of carbon saturation, because there's this additional piling on of the carbon, right, that keeps coming and that keeps building up the soil depth and readjusting, if you will, the saturation point of the soil every time that happens. Does that make sense?
That's super interesting. Thank you.
Yeah.
So you mentioned deep soil. That's also a very exciting and fascinating topic. And I know that you've been investigating soil carbon. Before I was picturing deep soil as I picture deep oceans, where there's no light. You imagine nothing really goes on there at those depths. And yet we've seen pictures of those amazing alien-like creatures that manage to live at the bottom of the ocean. So could you please talk a little bit about deep soils and what processes occur in deep soils, and do they happen at speeds that can still influence the climate?
Yeah, so to start with, if you've never thought about it, most people, I should take one step back, that a lot of the carbon data that's collected and that's out there is really biased towards topsoils. Typically the top 30 or 50 centimeter rarely covers the top 100 centimeters or a meter of soil, but there's very little data actually on soils that are deeper than 1 meter. And so our understanding so far is biased towards topsoil. And there's a good reason for that. Topsoils are easier to study. That's where more of the carbon and biological activity is, and that was the case. But we know that soils don't end at 30, 50 centimeter or even a meter. They can be very deep for many different kinds of reasons. It could be because soils are highly weathered, so extensive both physical and biogeochemical weathering can cause this. Both examples of this you could see in the two figures on the right here, for example, one from our study systems in the Sierra Nevada, and another one from Asia. Then the other one that you see on the left-hand side is actually a soil where a wind-blown material that was transported on about 12,000 or so years ago in the central part of the US. So this is all more than 6 meters deep less, that has buried the original soil layer that's marked by the dark layer there. And so soils can be really deep for many different reasons. And the depth of soil is governed by, CLORP, or the state factors of soil formation, climate, organisms' belief, paramaterial, time. We don't have time to go into that, but it's important to think about a whole soil profile when we're accounting for carbon. And that whole soil profile that includes the A, B, and C layers, the weathered part of the soil, right? The D or R is excluded here because that's the unaltered bedrock. That's where the parent material is. But when we're doing this accounting, then we have to be mindful about how deep is that soil, which could be very different even from this example, from a fairly old paper at this point. And there could be carbon that makes it that makes its way into these deep soil layers for many reasons, because deep roots make it to that layer and deposit, because there's bioturbation by roots and other organisms that could put carbon in deep soil layers, because water moves down soil layers through pores and fracture networks, and then it takes carbon down with it. We know that frost churning or cryotubation can do the same in Arctic ecosystems, and we know that all sorts of transport processes by wind, by lists, and even deposition of fresh ejecta from volcanic activity can bury soil after layer, creating this really deep soils. And so in my lab, we had this long-term study that we've been doing as part of the Southern Sierra Critical Zone Observatory, which is basically located on the western slope of the Sierra Nevada. And for those of you who don't know much about the western slope of the Sierra Nevada, it's a climosequence. Soil properties change as a function of climate. And when you get to the middle of the band, it's an environment that has optimal temperature and precipitation conditions. It's warm but not too hot. It's wet but not too cold, right? So soils have weathered, optimally to depths of 4 meters that you see in subroot, but all the way down to even 10 meters in the Providence ecosystem. And I want to make sure we are clear about the fact that that dark layer represented by CR here is actually weathered bedrock, what we sometimes refer to as saprolite. It is part of the soil, but it's a little harder to sample. So we had not actually previously included this layer in our accounting of how much carbon is in soil. But if you just plot, now represented in the bar charts, how much carbon actually has accumulated in the A and B, so the more unconsolidated weathered layers of the soil versus the subrock or the weathered bedrock, there is quite impressive amount of carbon stored there. So the amount of carbon stored in the weathered bedrock in Providence, the dark bar in the third point here at 2015 elevation, is more carbon stored in the weathered bedrock, in the saprolite, than there is in the entire soil profile of the lower elevation site, which is in the Central Valley of California, basically an oak savanna ecosystem that actually has a decent amount of carbon. And it's even very close to all the amount of carbon stored in the high elevation system. And the amount of carbon stored in this weathered bedrock that we had previously not included in our accounting of carbon stored in soil can be almost 30% of the soil's total carbon storage, And if we just use below A horizon as a way of defining what's topsoil and subsoil in this ecosystem, more than 70% of the total carbon of this Providence ecosystem is stored in the subsoil, not the topsoil. This is something that people like Rob Jackson, for example, try to pay attention to and get people's attention to many years ago, right? The new thing we're adding here is that we're not just quantifying the deep B horizon soil carbon, but rather even going towards C horizon and including that part of the puzzle. And using some really rough global approximations of how significant is this likely to be in global carbon accounting. If our assumptions, that I will put it out there, are really, really general, if our assumptions hold even to any degree, that's additional 200 gigatons of carbon that's stored in weathered bedrock that it doesn't show up in anywhere of our global accounting of carbon right now. And the paper that reports this, I'm glad to report that as of this morning, is officially in press at ERL. So it should be coming out any minute now.
Congratulations.
Yeah.
Okay, that's fantastic. Very, very interesting. That's right. But before we move to, I have a couple of more personal questions. I would like to ask, going back to the issue of soils being a natural climate solution, in order to really be a nature-based solution, soils will have to accumulate and stabilize carbon quick enough because, it's a very urgent matter. So obviously we can destroy soils and the carbon contained in those soils very quickly, but can soils stabilize carbon quick enough to be considered a viable climate solution?
Yeah, I think that will have to depend on what we mean by quick, right? Because as we've seen in a lot of the kind of historical soil data and studies, it's much easier and faster when soil carbon's being lost to soil, from soil to the atmosphere because of intensive management practices and other ways than it is to put it back in soil and to reclaim soils. And so there's definitely a lot, this is not a short-term strategy, let's put it that way. The benefits that we see in a year or two may not necessarily be huge, but if we stick with it, we know very well that we can accumulate a good amount of carbon in soil. And that is, in fact, the right thing to do for many reasons. I like to keep reminding folks that soil carbon sequestration is important and should be part of any sensible management strategy that is thinking about combining both natural and engineered solutions to climate change. But it is also a much bigger issue than that. It is about restoring soil health, because it's important for health of the ecosystem and the communities that depend on land too.
Thank you for answering that. So before we move to the Q&A section, I would like to ask a couple questions. One is that what's the legacy that you would like to leave in the field, in science, but also beyond science?
So let's see, the legacy I would like to leave.
Yeah, we made this question to Josh last month. I think the answer was interesting. So we want to implement this as a question to all the invite speakers. Yeah.
Yeah, no, I hope my legacy is that I thought of as a scientist and educator who cared about everyone and who cared about the right things, regardless of how difficult doing the right thing might have been.
That's a great answer. Also, something that I'm curious about is, when did you decide to speak up, become a leader, an activist in discussions about race and racism? What changed in your mind to that made you speak up?
I think my experiences, frankly, forced me to be vocal about it. But like most people, when I was a grad student, postdoc, or pre-tenure faculty, I didn't have the privilege of speaking my mind. I didn't have that luxury, right? I worry about job security like everybody else. And so we limit our actions in these kinds of topics that can sometimes be tricky. But job security, tenure is a wonderful thing. It removes those barriers, right, from doing the right thing and talking about issues that matter, issues that affect a lot of people, and a lot of people. And I think my decision to speak up had a lot to do with, as I said, my own experience, but had a lot to do with also experience of people, especially in at least one of the institutions that I experienced some difficult situations, even decades after I left, where nothing really changed for people that looked like me. And that was disheartening. Somebody needed to shine a bright light at these issues. And it's not going to be the junior scholars that are at that institution at this point. Many of them will talk to you if they trust you, and they will tell you their experience. But they can't, even if they are rather vocal on general issues of equity and injustice, they can't obviously shine a bright light on exactly what's happening and who's doing what, and how the institution should be responding to things, to issues related with justice. So I felt that I had a responsibility, not just to my young self that had to struggle through some of these systems, but also to the folks that are in the system right now, and that hopefully the future generations that will follow us, that we get our act together already. We are, at least me, I can't say that for you, General, necessarily. I'm part of a public institution of higher learning. I get to do the work that I love because of a diverse group of taxpayers paid their taxes and made this job possible for me. So serving that public and giving equal access to higher education to everyone that represents that public is not a favor I'm doing to anybody. It's literally part of the job that I'm paid to do. And I think it was important for me to be clear about that and speak up about that.
Thank you, Asmeret. You are clearly an inspiration for many of us, and not just scientists, but everybody all over the world. So, Asmeret, what advice would you give to them, to the people you inspire, especially young girls without resources that want to change the world?
Yeah, a couple of, I think, important things that have made a difference for me is reading and learning about the world around me and seeking education as much as possible, right? Because I think, there's a lot of challenge in the world, many more challenges we all will face going forward. Nothing is guaranteed, but if we work hard and we read and we grow, intellectually, and we grow intellectually and we learn more about our world, then we are able to then have that only kind of lasting worth that anybody can guarantee in this life, which is education. And that's, that can also take us places, help us achieve our dreams. There's not much else guaranteed in this life. Challenges are part of the deal. But if we are, if we stick with education, stick with learning about our fields, about the world around us, how to navigate that world, how to, and when we work obviously to surround ourselves with supportive colleagues, then achieving our dreams becomes that much easier. And I think that's my advice to people is be fearless about reading and learning about the world around you and learning just all the time, right? Growing and working, being purposeful about surrounding yourself with a supportive community of folks.
Thank you so much for sharing. So we are now moving to the Q&A section. So please feel free to type your questions. But I think Pierre Gentin raised his hand before, and also Glenn. So Pierre, feel free to unmute yourself.
Yeah, thanks. I think you partly alluded to that. So first of all, thanks for the great talk and all of the comments. And yeah, it's great to also hear your experience also on the diversity front. My question was actually related to steady state, which I think is very interesting because the mitigation strategy has many different timescales. So, and you alluded to some of that. So I was wondering, especially given the soil timescales, and for instance, there's a lot of discussion also on reforestation, maybe on shorter timescales. So, and I feel there's a lot of confusion out there as to what is the potential of land to some extent, which is very dependent on the timescale we're looking at. And I think, or at least that's my feeling, is that I don't know, it's dangerous in some ways, what we hear sometimes. I think you were very clear today, and that was great. But sometimes we hear things where we could all solve the climate crisis with just land, and that's very dangerous because it means that, of course, it's like different layers and we need to drastically reduce emissions. So I would love to hear your thoughts on that, like on the different timescales where you see maybe a soil component, like the reforestation, etc.
Yeah, so as we talked about a little bit earlier, right, the natural climate change solutions, we have to be realistic about the potential we can achieve, right? Even the upper limit, as discussed in the 4 per mil effort, is a third of the offsets that we need. Even that might be a challenge, right? So I think it's, first of all, really important to be those kinds of upper limits of what we're talking about. And I don't think it's helpful to the conversation at all when you, as you put it really correctly, to give anybody any message that all of these climate problems can be solved if we just took care of these natural climate change solutions. And in some ways, that kind of approach can even serve an unintended purpose of giving cover to people who do not want to actually reduce the emissions. And so this is why I try to be really super clear about, we cannot, it's non-negotiable that we have reduced emissions, but it's also non-negotiable that we include natural climate change solutions in the mix. But we can't substitute natural climate change solutions. There is no realistic path forward there to just achieve what we need to achieve with natural climate change solutions. I think that's really important. And it's also important to keep in mind that the benefits that we get from natural climate change solutions early on is going to have to be small, relatively speaking. The full potential cannot be achieved right away. We're at least a decade, if not longer, out from where we can achieve those optimal climate change benefits, natural climate change benefits for reducing the atmospheric burden of CO2. And so those timescales are important. The keeping a clear sight on the fact that we have to do both of these things, not one or the other, is, I think, to me, extremely important that we have some clarity. There's a lot of business and political interest on this topic at this point, right? And so I feel like some of the confusion comes from folks who are so eager about, doing one thing or another, that, I'm going to applaud more people being interested in soil, but I also think it's extremely important that we are clear and realistic about what we're communicating here and what is the scientific basis for this, for the things we're talking about, right?
Thanks so much. Yeah, thanks again.
Thank you, Asmeret. So I think next is Glenn.
Hi, Dr. Berhe. Thank you so much for your talk. I wanted to comment on, you had sort of grassland, like prairie management and cropland management as contributing to, or being able to sequester maybe something like 4 combined petagrams of carbon. But also, isn't there a hidden additional benefit in that you transform these agricultural practices from carbon emitters to carbon sinks?
Yeah, you're 100% correct there. Yep. There is the benefit of avoided future emissions, plus the benefit of actually drawdown of CO2 that's in the atmosphere right now. You're 100% correct. Yep.
Awesome. Thank you.
Thanks.
Okay, I think also soon ask in the chat box, what status would you call a soil healthy? In what status would you call a soil healthy?
Yeah, so this definition of soil health becomes a really interesting topic of debate all the time, because it's a purposefully vague term, right? That refers to the ability of a soil system to continue to support the functions that are critical for a vital living system, right? So for not just human, but also all the living entities, and support life and conduct all the related life processes, which then becomes important then to use indices for us to explain soil health, right? Because if I'm going to answer your question about in what status would you call a soil healthy, I would say it's a soil that has, let's start with the topic of today, a good amount of organic matter, supports a thriving population of microbes, and where, the biogeochemical cycles of essential elements is carrying out with a in a way that the nutrients and critical elements in soil are not being lost. Plants are able to grow and thrive in that ecosystem, as well as microbes, and so on and on and on and on, right? And so I would say the state of the soil ecosystem right now is really bad by most accounts. At least a third, if not close to a half of world soils are considered degraded, meaning their capacity to support plant production is actually compromised, largely because of human actions that in agricultural systems through deforestation and similar activities. I don't know if that answered your question, but I'm happy to go into detail about some analogies and ways that, I think it's helpful to think about the soil health discussion.
Soon, feel free to follow up. Otherwise, now we have Rahul Kashyap, and then Charles Harvey. Rahul?
Hello, sir. Hello, ma'am. Just I have a small question. Like, since we know that everything like vegetation grows on soil, in the recent scenario, we have that global warming context that vegetation is being degraded. So, what is climate change implication in the soil which is impacting vegetation, and how can we like stop it or reduce its impact?
So let me see if I can rephrase your question. So there are many ways that global change and climate change in particular can affect soils. So for example, if in areas that have experienced considerable warming in the last few decades, for example, we've seen considerable reduction in carbon storage, which not just affects how much carbon stored in soil, but also ability of that soil to support plant production. And even, these ecosystems have even seen shifts in vegetation patterns. So not just productivity, but also, which plants are able to thrive in a given ecosystem and the like. But the impact on the plants and the way that soil mediates the impacts that plants are likely to suffer really depends on the specific climate change mechanism we're talking about, its extent, how long it's been going on, right? And all of these other related variables.
Also, like, what are the key drivers impacting these changes in the soil and soil carbon? How we can study them?
I mean, some of the key drivers, as we've said, are how these changes in climate, say, for example, are affecting plant productivity, the way that plants are contributing to carbon stored in soil, how it affects microbial activity and the resultant decomposition of carbon, or even how can it affect the association of organic matter with minerals that might have implication for how long carbon can stay there. So all of these things that we talked about, for example, in the discussion, can be affected by climate change with the resultant implications for plant growth. Keep in mind that soils that have a lot of carbon tend to support a high degree of plant productivity. Generally speaking, that's because there's a lot of not just carbon, but also nutrients tied into that vegetation, right? In the organic matter, I should say. And when that organic matter decomposes, then it releases plant essential nutrients into the soil that supports plant productivity. So the implication of altered rates of decomposition doesn't stop just at carbon storage. It has important implications for plant productivity and everything else that depends on that, kind of plant soil system.
Do we like have any global data set, satellite based or something which or model based which we can use to study this soil organic carbon?
Oh yeah, there's a whole world out there. I'm pretty sure the folks who do soil science right here in your institution can point you to many.
Okay, and thanks a lot.
Or you could let me know an email and I'm happy to help you too.
Okay, so now Charles Harvey.
Thank you for the excellent talk. I really enjoyed that. I want to ask a question that is sort of adjacent to your talk, though, because I'd be really interested in hearing what you have to say. I've been hearing a lot, particularly in engineering departments around here, about biological, BCCS, biological carbon capture and sequestration. So the idea that you get around these timescale issues by burning the biomass, producing carbon dioxide, separating it from the nitrogen and injecting it way below the soil so it stays there for a long time. What do you think of that? Is that do you have any thoughts about that?
Yeah, so that's definitely in the horizon. A lot of folks, especially in the engineered solutions approach, and it includes not just what you described, but also engineering, kind of engineered plants to that could achieve carbon sequestration better, supposedly, and also the charring and pyrolysis process gasification, where the CO2 is trapped and injected, as you indicated, and in some cases, even returning some of the residue, the pyrolyzed residue from that product into soil in a way of to promote basically better nutrient and water holding capacity, i.e. carbon storage at some level. I'm of the opinion that at this point, we don't have any luxury to ignore any possible solutions. So I'm all about people trying to see and ascertain really the feasibility of what can be achieved by these different approaches, right? Just being super clear about what exactly is the potential here, which I think in some ways is still a question with some of these approaches that are covered under the umbrella of BECCS. But it's, as you've clearly alluded, that's not necessarily in my wheelhouse. So I wouldn't know that I want to say anything more than that.
Okay.
at least with certainty, right?
Yeah. Okay. Thank you.
Thanks.
Okay, I think there are no more questions, and we are right over an hour, so that's fantastic timing. Okay, so Asmeret, thank you so much for accepting the invitation to talk. So Charlie is applauding, and so am I. Thank you so much. It was a really great talk. We had a lot of fun, and we really enjoy having you here. So thank you so much. Best of luck with your future projects. Hope to see you soon.
Thank you so much, everyone. Thank you.
Thank you.
Bye.